so much for coming for the 7th lecture in network security. So as we saw last time, we started with the real algorithms to explain this, triple this, double this last time, and you have seen how we built it from inside, right? So maybe one time you'll come yourself with your algorithm that you could propose, and the government will take, and will call it after you. Just the idea. So this started a long time ago. Maybe it's not very much used now. It's replaced by the AES. We're gonna explain today. Okay. This is a FISL algorithm. This is non-FISL algorithm. We already know the difference. And today we'll explain AES. How is it designed from inside, and then we analyze it like we did with this. Weak keys, strong keys. All of that. So ES basically now is used everywhere, and I'm sure that you have used it. There's 3 versions, kind of, depending on the size of the key, as we'll see. All right. So as you see, we started very smoothly, very nicely. We start from the basic concepts about network security. We have covered some math. Then we start talking about the components, the XOR, the shift registers, the P boxes, straight, compression, expansion, permutations, and all of that, just to prepare you when you study the real algorithms, you understand what's happening there, right? And now, from now on, what we cover is a real thing. It's a real thing, not a theoretical thing. Maybe in a few lectures we're going to go math again to give you some concepts, all right? So as you see, and by the way, as we go, so you'll see that we're going to cover security in all the OSI reference model. So in OSI reference model, what do you have? Application, transport, network layer, physical layer. So we're going to cover all the security, all the 3 layers. Okay. So you'll have a lot of information at the end of this class. All right. Just and from the lab, you'll know a lot of practical stuff. You learn about applications, about configurations, about threats, about security and all of that. So I'm sure that this will get you in a good foot after you finish this class in network security. Okay, so I'm not sure why this is not. For a reason, this is not working. I'm happy. All right. So we're going to talk about the history of AES. What did make it some of the lights off? Maybe it's nicer like that. All right. So then we define the AES. We'll talk about the transformation used by AES. Then we'll explain the expansion process. Then we'll see different implementations. All right. So we'll be covering that all the time. So first of all, the advanced encryption standard is a symmetric key block, exactly like this. So we're talking about block. We are encrypting block by block, and it's symmetric. Symmetric means what? Symmetric means one key, one private key are used. All right, and it's been there, I think, from 2001. So it's been for a while also. All right. So in February 2001, NIST announced that they need to have a proposal for a new encryption protocol to replace this. So a few proposals came, and this was selected to be the finalist and then adopted by the government. So there is 3 conditions. There's 3 requirements are required from the government for the new algorithm: security, cost, implementation. So it will be very secure, cheap, and the implementation could be in software and hardware. It will be very easy to implement software and hardware. All right. As we have learned, all of these protocols built of rounds. So in this, how many rounds we have? Anybody remember? 16 rounds in this. So in here, how more or less you think it's more secure, but it's more rounds or less rounds? Can you guess? Should be more. It's less. Okay. All right. So So it's a non-fissile cipher that encrypts and decrypts a data block of 28 bits. So what was the data block in this? 64 bits. Here 128 bits. It uses 10 or 12 or 40 rounds, so 3 versions of it. The key size, which can be 128, then we use 10 rounds. 192 we use 12 rounds, and 256 14 rounds. Remember in the last class we said the larger the key size, the more secure is the protocol, at least from for brute force. So how many? If you have 256, what are the options for the keys? 2 to the power 56, right? Yeah. So from that point of view alone, it's much more secure. So there are other factors. So if you say in this, for example, in this we have how many? 64 bits, right? Right. So how many options we have? 2 to the power 64. Okay. But now this is in this, right? In AES, how many we have? It's like 128 bits, okay, or 192 bits, one version, or 256 bits. So how many options for this? We have 2 to the power 256 different keys. So definitely it's much more secure. The larger the key is, the more secure. All right. So ES has defined 3 versions with 10, 12 rounds, and there is 10 rounds 128-bit key, 12 rounds it's 192-bit key, and 14 rounds 256. We'll see the design how it will happen. Okay. So that's the block. Let's take a look, and you know our way. We look at the general picture, then we go deep. How is it designed, right? So the general design for ES, as you see in here, it starts with 128-bit plain text, and will give you 128-bit ciphertext. All right. Inside it, okay, it will start with something called a pre-round transformation. Then after that, we have 10 or 12 or 14 rounds. Remember in here we said 10 or 12 or 14 rounds. So there is one more extra round at the beginning. All right. So what is the size of the key? Either 128 or 92 or 256. So we have the key expansion, and always the key expansion will give you 128 bits. So if it's 128 bits, it will give you 128 bits. If it's 192, it will give you 128 bits. If it's 256 bits key, it will give you 128 bits, right? How many keys is it gonna give you? Number of rounds plus 1, because we have extra round. So we start from key 0 to key NR, which is the number of rounds. What is the options for the number of rounds? 10 or 12 or 14. What is the option for keys? 128 bits, 192 bits, 256 bits. Clear? All right. I'm not sure what's happening in here. I don't need you. Not now, please. I don't need you. Okay. All right. So we have round 1, 2 until round NR. Okay. And K0, it will go to the pre-round, and K1 to Kn, depends on the round, you're gonna go there. So if the number of rounds is 10, then it's 128-bit. 12, we said that the relationship between the number of rounds and the key. Okay, so that is the algorithm. So what we need to do, we need to go inside this, we need to go inside the rounds, we need to go inside the key expansion. Okay, see how they are designed. Shall we go? Let's go. All right. So as introduction, okay, data units used in ES. So you have the byte is built of 8 bits. Okay, byte. So there is something called byte. We can explain it. Word, block, state. All right. Terms used in ES: bit, byte, word, block, state. So the byte is built of how many? 8 bits. Could be one row, or could be one column. If it's row, it starts from B0 till B7. If it's a column, it starts from B0 to B7. What is this? Byte. Let's go to the word. Word is built of how many bytes? 4 bytes. So byte 0, byte 1, byte 2, byte 3. So how much total bits is in the byte? In the word, how many total? Bytes? 4, right? And each byte is how much? 8 bits. So 8 times 4, how much? 32. Then you come to the block. The block is built of 4 words. 4 words. So word 1, word 2, word 3, word 4. That means it's built of how many bytes? 16 bytes. From byte 0 till byte 15. Alright? Now we're going to come to the state. What is a state? Is a word, but it's built in the 4x4 matrix. 4x4 matrix. So as you see in here, so in here so the first 4 in here gonna go as a column. The second 4 here comes as a column. 4 as a column, 4 as a column. So state is built of word 0, which is in here, word 1, which is here, word 2, which is here, word 3 is here. Alright? So that's how is the structure. You have just to pay attention for this structure. All right. Okay. So the block to state and state to block. So we'll be able. It's very easy. You don't have to explain it even. It's very easy to convert from here to here, from block to state, or from state to block. You could write a simple algorithm in the program. So block to state, this is a block which is built of 16 bytes, 4 words, word 1, word 2, word 3, word 3. So how you do it? You take the first 4 and you put them here. The second 4, you put them as a column. So it goes like that, and go like that, then that. Alright? Very easy. Alright? If you need to convert the state to a block, the same thing. You take the first column, you put it here. Second column, next. Third column, next. Fourth column, final. Okay? So know how to convert from state to a block and from block to a state. Alright, so maybe this is an example. Okay, so what is this? A block. A block. The block has to have how many bytes? 16. Unfortunately, we are short 2, so what we have to do? Padding 2. Alright? So you convert them to hexadecimal, whatever this is hexadecimal. So how you do it? You put like 0, 0, 0, 4, 12, 14, and then you go the next 4 here, the next 4 here, and here. Very easy how to convert from block to state and vice versa. Alright, so let's take a look at the structure of the round. We're gonna take off the round. So what we are doing in here, we're putting our input as state. What is the input? What is the size of the input? 128 bits, which is how many words? How many bytes? 128 divided by 8, how much? 16. All right. 16 means how many words? 4. All right. So it's like, you start with a state, which is 4 by 4, 16 bytes. So the box, the input text, you're gonna divide it into 16 bytes. You put them where? In a state. Okay? So it will be 4 by 4 state, right? And the first process will have sub bytes. We're gonna explain what you do in here. Then it's gonna generate a state. Then we're gonna do shift rows. You're gonna generate a state. Then mix columns, generate a state. Then it goes. So you start from a state, you end up with the state. All right. So how many operations we have? 4 operations. Who said 4? Very good. What is the difference in the last operation? It's a keyed operation. We don't use the key. we don't use the key, we don't use the key, we use the key. So let me repeat. States moving from, this is the starting, gonna go in here, there's 4 operations, the last one is a keyed operation, we're gonna use the key with it, right? Alright, so one add round key is applied before the first round, and the third transformation is missing in the last round. Okay, we'll see it, okay. So let's take a look at the transformations. So through this, remember our goal in encryption to cause what? Confusion and diffusion, right? So to do that, what we did, we do substitution, okay, and we'll do permutation, and we do mixing, and we do key adding. All of this will blend the data very well. We'll see how we do that. All right. So to provide security, ES uses 4 types of transformation: substitution, permutation, mixing, and key adding, or key adding. All right. So let's take a look at the first block. What is the first block? This one, sub byte. In the disk level, if you remember, in the disk we were looking in the bits level, right? In here we work in the byte. So switch byte with a byte, not bit with bit. Byte with a byte, we change the byte. Okay, we don't go to the bits level yet. Okay, so in the sub byte, the first transformation, sub byte, is used as the encryption side. At the encryption side, to substitute a byte, we interpret the byte as 2 hexadecimal digits. So the byte is a hexadecimal. The byte is a hexadecimal. It has 2 digits, right? In the byte. So 1 for columns, 1 for rows. Okay, so let's take in here. So in here, for example, right? Remember we have the state. The state is 4 by 4. Right? 4 by 4. Total 16 bytes. We take the byte in here as a hexadecimal. Okay, so that's the state. So let's say this one. This is, for example, whatever it is, 2 digits. Let's say 24. All right. So the 2 will go to a table, a pre-designed table, and it will be row number 2 and column number 4, and we'll take the new value. Okay, and then we substitute it back in here. Let's take a look. So this is the table. Okay, so the table is from 0 to F, and the column is from 0, the continuation here, from 0 to F, right? So let's take example. Okay. So this in here, we need to convert it in here in sub byte. So let's take the first one. What's the first one? 0, 0. Let's go to the table. Where is 0, 0? Here. So 0, 0 becomes what? 52. Can't see. Is 52 or 63?
52.
52.
Oh, here. Okay, that's the sum. So 0, 0, how much? 63. 63. You see it in here? 63. So let's take 12. Let's go to 12. 12, 1 and 2. 1 and 2 is C9. C9, and so on and so forth. So that table is already given by the designers. Alright? Clear how we do? So what we did in here, we replaced all the bytes with a new byte. Alright? In the reverse, very easy. We're going to go to the other table. Let's take a 63, right? This is the reverse table. 63. Where's 63? 6 and 3. What's 3 in here? 0, 0. It reverses it. Okay? So, alright? So we are talking here about, let's go back in here. We're talking about where? Here. Is it clear? So we could do this operation through a table, I'm sorry, or through a mathematical operation. Alright, I explained the table for you. I'll keep the mathematical operation for you to discover it. Okay, just read it and you'll know. Okay, so you could do it through the table in here. Okay, or you could do it through the transformation using G power 8. Okay, and that will conclude the subbytes and inverse subbytes transformations. All right. So in here, so when you see how it goes, this is the other way, the mathematical operation using the GF2 to power 8 field. So take a look at it. What will happen is you'll have the state. You'll create the matrix, and you know a matrix by design which has inverse, and you do the reverse operation. Just take a look at it, okay? But table is fine. You could out of table, or you could do the mathematical operation. Why mathematical operation is useful? To build it as chip, as hardware. Remember, one of the requirements is to be able to implement it as hardware and as software. All right. So in here you could implement it as a hardware and a software. So this is the algorithm. Okay. Then, so number 2, permutation. Number 2 is permutation. So another transformation found in shifting, which permutes the bytes. So we need to permute the bytes. And this is we're talking about, sorry, I keep going back and forth. I want to make sure just you are following. Okay? I'm talking now where shift rows. From the name, what we are doing in here? Shifting rows. In the first one, what we did with the bytes? We changed them. In here, what we're doing? Shifting rows. Okay? Alright? So shifting rows. So what we'll do in here, in the in the encryption, the transformation is called shift rows. So basically, you're gonna have shift left, shifting. In the row number 0, there is no shifts. You don't shift in the row number 0. In row number 1, you have 1 byte shift. In number 2, 2 byte shift. In number 3, 3 byte shift. As simple as this. No shift, 1 shift, 2 shifts, 3 shifts. Can be any simpler than this? Cannot be any simpler than this. Okay? So that's it's a very simple algorithm. Let's take example. The first row, how many shifts we have?
0.
No shifts. In the second one, 1. In the third one, 2 shifts. In the fourth one, you see, it's like in here, 3 of these are shifted in here. Okay, you have the 3 shifts. All right. So in the second operation, we do shifting. It's a blue in here, these are blue, but it's not clear, but you can figure it out, right? Alright, then number 3 is mixing. Mixing. We are blending the data now. Okay, so we need to enter byte transformation that changes the bits inside a byte. Alright? So now, in the first 2 steps, we switch bytes. Right? Now we're gonna go into the bits and try to switch bits inside it. So based on the bits inside the neighboring bytes, we need to mix bytes to provide diffusion at the bit level. All right. So for example, if you look in here, this is the data x, y, z, t. You're gonna have a constant matrix by design. Okay, and then you're gonna multiply the matrix. You know how to multiply the matrix. So a times x, then b times y. So ax, by, and now you have a new matrix. So now you are changing the bits, not only the bytes. Why? Because you are multiplying matrix to the matrix, producing a new matrix. So the bits will be different. The bits will be different, right? So for example, you could take this as a constant matrix, and this is the inverse for it, right? The inverse. So if you multiply this by this, what you get? If you multiply a matrix with its inverse, what you get? The identity matrix, right? Matrix, right? All right. So what will happen in here? So for the column mixing, you take the first column, right? You take the first column, you multiply it with what this. You take any column. So you start with the first, second, third. In here, we're taking the second column. You multiply it with what? With a constant matrix. Will give you a different column. You replace it where? You put it together. You do the same thing with the second column. Same thing with the third column. Same thing with the fourth column. Okay? Alright? Blending. Not dancing, blending, right? Okay? Alright, so, and the reverse, it will be a reverse. Can we do the reverse? Can we do the reverse? Yes, why? Because we have the inverse of this. Right? So we have the inverse of this. Alright. And this is the, so in here what will happen? So you have this in here, this column became this column. How did we get this column? How did we get it? By multiplying by a constant matrix. Right? And replacing that. Alright, the question is, how did we know that we are mixing the bits, not a byte level? Look in here. So for example, let's take a look if there is two similar. Oh, in here 63 and this is 63. In here change to what? 62 and here 92. So we are now mixing in what level? Byte or bit? Bit level. Bit level. So two similar bytes, when they changed, became completely different. Alright? So then the last stage, adding the key. Adding the key. So add round key proceeds on column, add the time. So what we do, let's take a look in here. So adding the key, what will happen? So you have the state, let me go back, just to refresh your memory. It's very important. You know what should I do? I should make a picture, I should make a photo of this and keep it in every slide. Because that's how it proceeds, instead of going back and forth. So we finish this, substituting from the table, then shift rows, then we mix the columns, right? Now we are here, what we are doing, we're adding the round key, the last stage. Alright? So in the last stage in here, okay, where are we? Last stage, here. So what we do, you take this one, okay, and you take the first column from the key. What is the size of the key, by the way? 128 bits, always 128 bits, right? Okay, and you built it in a state. State will be 4 by 4, right? 4 by 4, 16 bytes. So you take the first column from the key with the first column for the data, okay, and then what you do, add them up together. Okay, and you take the second, the third, and that's how you mix the key with the data. Mix the key with the data. Okay. Alright, so let me one more time refresh your memory and focus on this figure very well. Okay. So what we did, we formed the data in a state. That's our data. What's the size of the data? 128. Okay. Now, in the sub-byte, what we do in the sub-byte and this process in here? We change each byte according to the table. We divide the byte in 2 digits, column and row number, and we pick it from a predefined table, right? Then we have a state. So we mix here which level? Bytes level. Then after the shift rows, what we do in the shift rows? Shift. The first row we shift how many times?
The first one we don't do.
No shift.
The second one we do it once. Third one twice. The fourth one 3 times.
Thank you. Okay, then we have a state is mixed. Then we come in here to the mixing columns.
Take a single column and multiply it with the matrix.
With the constant matrix,
And replace
the column with the new column, right? Then we have a state. Then add a key. What we do with the key? This one, what we do in the stage in here? Add the key. So the key will form it like a state, okay, 4 columns. So we took the first column from the data, we added to first column from the key. Second with the second, third with the third, fourth with the third. And then we have the state. That's how is
So like one question, like this mixed columns and add round key. So do we have to, like suppose we have 4 column in a matrix, right? Do we have to mix only 4 columns to the constant matrix, or just we can do one column or second column?
Okay,
So the data,
So, okay, so the data, for example, the data, so the data is matrix 4 by 4, right?
Yeah.
So it will be like this, right? Y, 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 Z, 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 T, 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 right? And the same thing, the key is 28 bits. So also you make it 4 by 4. 4 times 4, right? Okay, so, you know, whatever. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4. Right? So you take the first column in here, okay, you add it with this column, add it, right? And the result where you replace it where? In the first column. That's it.
No, my question is like, we are adding first column of the data with the key.
Yes.
So do we have to add all the 4 columns of data?
All
with
of
the
them.
key?
So you're gonna add this with this, replace it here. You're gonna add this with this, add it here. Add this with this, add it here. Add this
Yeah.
with this, add
So
it here.
that, I mean, the 4 steps
4
are
columns,
finished.
yes, 4 operations.
Oh.
4 operations, okay? All right, so now where we have to talk now, which part we are missing? Oh. We're missing this section, right? So the key in here will be changed to 128. So how many keys we generate? 11 in this case, or 13 or 15, right?
Yeah.
Okay, so we finished all of this. We have to talk about this one, the key expansion, right? Quickly. So in the key expansion, what you do in here to create the round keys, okay, we have always to have one more than the number of rounds. So if we have 10 rounds, we're gonna have 11, right? All right, so what we do, okay, the pre-round, okay, we're gonna have how many words? Word 0 to word 4. Round 1, word 4 to word 7, until depends on the number of rounds, so it will have like the last 4 rounds. So the question, how we calculate these, right? Okay, so each word, how many bits? How many bytes? 4, right? 4, okay, so each here, 4 times 16, how much? 128, right? So times 32. 4 times 32, 128, right? So 128, 128, 128, until the end, 128, right? So this is the pre-key, key 1, key 2, and then until key 10, for example, the first. So very easy. So you start with the original key. The original key, how many bits? 128. You don't form it as a state in here, you form it as block. We call it a block. So the first 4, second 4, third 4, fourth 4, right? So for the first one, you take the word, this is word 0, word 1, word 2, word 3. So the first key will be the same key. The pre-key will be the same key. Easy. Right? It will be the same key. Word, right? For the next one, so what you do, you take word 0 and then XOR it with the temporary value. We'll see how to calculate the temporary value, and that will give you word 4. So what you do, you look at here. So word 5 equals to what? XORing. Okay, the word before it and the word above it. The word before it and the word above it. In here, for example, how you W10. So it would be XORing the word above it with the word before it. Where is the problem? Is the first one does not have nothing before it. So we have to come with temporary 4, temporary 8, temporary 40, right? Okay? Temporary, okay? And that's how we do. So how we come with the temporary 4 is very easy. So temporary I, which is temporary 4, equals word 3. Let's talk about T4. Let's here TI. Let's say it's 4. Okay, TI is T4. So it will equals word 3. Where is word 3? There, the last one. Okay, you're gonna go rotation forward the process, then you do subword another process, and then you XOR it with another value. We'll see how to calculate this value, and we'll give you temporary. So bottom line, let's summarize this. So we start with the key as a block. The first 4 words coming as it is. Then after that, for each word, it will equal the XORing of the word above it and with the word before it. Right? So the problem is the first ones, they have nothing before it, so we have to come with the temporary what? Words. Temporary 4, temporary 8, until temporary 40, right? How to do it? We're gonna have this, we're gonna take a look. That's the process. Alright? So, the making of TI, temporary words, I equals 4 times NR. So NR, the number of rounds. So if the number of rounds are 10, so I equals 40. Okay? So let's take a look at this process in here. Okay? So the R constant. So in the round 1, okay, this is round 1, 0, 1. It's a preset. 0, 1 and all zeros. 0, 2, all zeros. 0, 4, 0, 8, 10. So it's a preset values. So if you are doing, for example, for this one, what would be the value of R con here? It will be this one. All right, preset, right, and so on and so forth. This is the key expansion. If you take a look at the key expansion, this is the algorithm. So in here, I'm not sure what happened here. So in here, table 7.5 shows how the keys for each round are calculated, assuming that 128-bit cyber key agreed upon by Alice and Bob. So this is the key. What is the size of the key? 128-bit. So in here, at the 0 round, okay, there is no temporary. Is there a temporary? There is no temporary, right? So what we do in here, so the first word in the round, you take the first part, which is 24, 75, A2 plus B3. That's the first part. Then the second word, the third word, the fourth word. We divide it in 4 words. So what is the key for round 0? The same thing. Alright? Then we do the process. Okay? So for example, this, what word number 5 equals to what? XORing this with this. XORing the word above it with the word before it. Alright? But we have, for the first one, to calculate the temporary keys. The temporary keys. Alright? So, as you see, this is as you go all the way to the end, and that's the key for round 10, that's the key for round 9, that's the key for round 8, and so on and so forth.
Can I do this again?
Huh?
Can you do this again?
Which one?
Go back, slide 27.
Go where?
To slide 27, go back.
Go to the next slide, you mean?
That's
Back.
7, exactly.
Back, back,
Back,
back,
back,
back,
back.
back.
Yeah, this one. Can you do that one again?
In here?
Yeah.
So that's exactly what we did. This is the key. Okay, take the first word 0 equals the first 4. Word 1 equals the first 4. Word 2 equals the third 4. And that's what we did in the table. We put the word 0, 1, 2, 3 as they are here. So 24, 70, 75, A2, B2 is here. Then we start in here 34, 75, 55, 88 in here. Then we start in here 31 and so on and so forth.
Okay.
Alright? And then after that, to calculate each key, you XOR the one on top of it with the one below it. What is the problem? The problem, this is nothing next to it. So we have to calculate the temporary keys.
Okay.
How we calculate the temporary keys using a certain formula that we explained. That's it. Alright. So in here, okay, each round key in ES depends on the previous round key. The dependency, however, is non-linear, and this is very important. If it's linear, it's very easy to figure it out. It's not linear because the subword transformation, the addition of the word constants, also guarantees that each round key will be different from the previous one. So let's test it. This is a test. The two sets of round keys can be created from two cyber keys that are different only in one bit. So in here, key, for example, key number 1, everything is similar except one bit. This key equals to this key except in one bit, so changed A to B. So these two different keys, there's only one bit different. Alright, so let's use them. When you use them, okay, when you use these, okay, the round key for set 1 and round key for, they are completely different, as you see, completely different, and the end is completely different keys. So changing one bit in the key, when you try to generate the other keys, you know, for rounds, are completely different. So diffusion and confusion. Alright, look in here. The concept of weak keys are not discussed here like we did in this. So look in here. So the pre-round is like that, all zeros. Okay, pre-round is equals to, if you remember in this, the key of zeros, is it a weak key or not a weak key? But a weak key, all zeros is a weak key, all ones is a weak key, right? So in here, if you have all zeros, in round 0 changed, round 2, and in round 10 it's completely changed. So it's not a weak key like it is in this. Okay? So always we could have a key expansion in 92 and 96. I'll keep it for you to figure it out. Okay? So the ciphers, ASE uses 4 types of transformation for encryption and decryption. In the standard, the encryption algorithm is referred to as the cipher, and the decryption algorithm called inverse cipher. Okay? So there is original design and alternative design. So that's the original design. So what we start with, okay, we start with add round key, which is this round key. Then you have the 4 processes: sub byte, shift rows, mix columns, and key. So this starts with word 0 to word 3, 4 to 7, and so on and so forth until the end. So how many rounds we have in here? 10 rounds. For 10 rounds, how many keys we gonna need? 43, right? 0 to, so 10 needs 40, and the first one needs 44. But we are numbering from 0, so it's from W0 to W43. How many words we need? 44, right? It goes to the second round. So you see similar boxes. In the last one, it's missing one box, which is mixed column. Okay? And in the decryption also, the last one is missing mixed columns in here to be able to reverse each other. Otherwise, you see, you start like this. You start from the round 1 to round 9 to round 10. Okay? And look at, we apply the keys in reverse, right? So we start from the last key to the first key. The alternative design is to have sub byte and then shift rows, and then inverse sub byte and inverse shift rows. Okay, you could do that. Okay. You could have mixed column, inverse mixed column, 2 designs, both are be good. Like in here, for example, so you have mixed column, mixed column, mixed column. So these are some examples to see the strength of. So look at this. This is a plain text. This is a plain text. That's the key, and that's the ciphertext. So completely different. Completely different. So the plain text is completely different from the cipher text. if you need to look at step by step how the state is states, right? Changing pre-round, round one until the end, the data keep changing completely different. So look in here. So this is the input state. This is the after the sub byte. This is after the shift rows. This is after the mixed column. This is the final. So every state is completely messed up, completely mixed up. Okay, so because that will have you will have like confusion and diffusion. So if we have all the plain text zeros like here, and you have any key, you see the ciphertext is completely different, completely different. Okay, and that shows it's very strong. Look in here, we have two closed plain text. So plain text 1 is all zeros. Plain text 2 is all zeros except one bit changed. Except one bit changed. So they are very close. When you encrypt them, I mean, if the cipher is completely different, that means it's a very good algorithm. So we're gonna use this key, previous key. You see the output is completely different. It's completely different. Right? So that tells you it's very good algorithm. Look in here, you have a plain text, but the key is 0. Remember, in the key and the this one, zeros or ones is bad, not good. In here, it gives you like completely different data. So that means it's not a problem. If you, for analysis, strength analysis of this, so the AES was designed after the disk. Most of the known attacks on disk were already tested on ES. Alright? So brute force, of course it will be stronger. Why? Because we have larger key. So ES is definitely more secure than this due to the larger key size. Alright. About statistical attacks, numerous tests have failed to do statistical analysis on the ciphertext. Differential and linear attacks also, they are not there. Alright, so for simplicity and cost, the algorithm used in AES are so simple, and maybe you notice it's like much simpler than this, right? Even when looking at it now, it's much more simpler than this, and they can be easily implemented using cheap processors and a minimum amount of memory. So you could have as 100. So that's famous AES that all of us used and use in many applications, many security. So we knew how to design A to Z, today. All right. And this is the second example for a block encipherment, block cipherment. Okay. Next week we'll see how we can do multiple blocks. We're talking now about one block. You have a block of data, fixed size 128. So if you have a big data, what you have to do, like a file or a hard disk drive, you have to divide it into blocks, and you have to apply the algorithm to it. So next slide we'll talk about 5 different modes how to do so. So that will be next class. Thank you so much.